Here we want to start with acceleration and use that along with some initial conditions to solve for position. So this example says, given acceleration a of t equals 2e to the t minus 12, with v of 0 equals 1 and s of 0 equals 0, find the position function s of t. So let's start by recalling the relationship between position, velocity, and acceleration. So we'll call s position, but remember s prime is velocity and velocity prime is acceleration. We can combine both of these essentially and talk about s double prime. The second derivative of position is also acceleration. That's another way to think of it. So we're essentially given acceleration here, an acceleration function, and we want to find the position, but the acceleration is two derivatives of position, so we'll essentially need to take two integrals to back out of acceleration to get back to position. And this is the way physics works, right? We're doing straight up physics here. This is essentially a mechanics problem, and this is how it goes. You're given the acceleration, and you do a little bit of integration to find the position. So let's do it. Okay, so we essentially roughly have velocity equals the integral of acceleration. All right, that's a very rough way of saying it, but I'll say it anyway. So v of t then must be the integral of 2e to the t minus 12 dt, but this is only as long as we plug in to solve for c using this initial condition of v of 0 equals 1. Okay, so taking this integral, remember the integral of e to the t is itself e to the t, so this is simply 2e to the t again, minus, well, it was 12, so now it's 12t once we take the integral, plus c, but we know that v of 0 equals, well, we're given that that equals 1, but when we plug in 0 for t into our velocity expression above, we have 2e to the 0 minus 12 times 0 plus c. We can now use this to solve for c. This tells us that 1 equals 2 plus c, so then c must be minus 1. Thus, we now have v of t. v of t is then 2e to the t minus 12t, and then we decided that c was minus 1, so we write minus 1 right here for c. Okay, that's progress. We went from acceleration to velocity. Now let's go from velocity to position. So roughly we could say s, the position is the integral of velocity. So more specifically, s as a function of t is the integral of velocity, which we decided was e to the, make that 2e to the t minus 12t minus 1. We'll integrate that all with respect to t. So dt there. Okay, integrating up, this 2 is just a constant, so it comes out front, leaving us with 2e to the t minus, well, 12t, when we do the power rule for integration on that, t becomes t squared over 2, so this all becomes minus 6t squared, because 12 divided by 2 is 6, and then minus 1 becomes minus t upon taking the integral, plus c. However, there is once again an initial condition for position. That'll allow us to solve for that c in the position function. So we have s of 0. Well, it tells us that this equals 0, but if we plug in 0 for t here, we get 2e to the 0 minus, well, all that middle stuff is 0, so minus 0 plus c. So that tells us that 0 equals 2 plus c, which then we can solve that for c. c equals minus 2. We now plug this into c in our position function here to get a final answer of the position s of t equals, and I'm just recopying all this, 2e to the t minus 6t squared minus t minus 2. And we've done something actually pretty amazing here, right? We have two little data points of velocity at a certain time and position at a certain time. And we use that along with the acceleration to solve for a position function. And what this position function would give us is where the particle is at any time t in the future. So knowing the acceleration here, which according to Newton's second law is essentially equivalent to knowing the force on a particle. That's what Newton's second law says, and I know I'm getting into the weeds a little bit here, but that essentially tells us as long as we know the force on a particle and a couple data points about its initial velocity and position, we can predict its position for any time moving forward. This is how we could get to the moon on Newton's second law, right? It's actually a very powerful amount of physics packed into this one little example here.